Welcome, everybody, to the last session of the CEV Fall 2020 workshop. And this is ordinarily the time we would have a short course, but that's not working out this year. But we did think hard about some recent trends we were seeing in a lot of the work that's going on at Penn State and outside of Penn State. And it's obvious that there's just a lot of new emphasis on applying machine learning and AI methods to a lot of different areas of vibration acoustics research. And it's part of the CEV's mission to bring those kinds of things forward to our sponsors and their community. And we put together, I think, an impressive list of speakers that span industry, Penn State academia, people outside the US. It's a pretty broad range of expertise as well. And we've got a nice pair of moderators here from Penn State, Dr. Carl Reichard and Danning Wong, to lead us first through quick overviews of the panelists' work and then an open discussion on a few key items, and then open items that might come from you guys in the audience as well. So we're hoping to learn a lot from this ourselves, in particular what industry and government thinks we ought to be doing in this area as far as teaching students, as far as doing research, what would help you. So this is as much for us as it is for you. So we look forward to the conversation. So Carl and Denning, take it away.
Okay, good morning. Danning, you want me to start?
Yeah. Right. Let me. Okay. So, right. Here's again the purpose of why we are doing this roundtable. A few observations. First, that apparently now AI and machine learning is getting more popular in our research, and also there are like emerging technical sessions in these major conferences in acoustics and vibration. And apparently the industry and the government are having growing interest and maybe hiring more people in machine learning. So here's why we are doing this roundtable. Want to discuss what are our common interests, what works well, what doesn't, and what are some challenges now using machine learning in our field. And then with that, we would like to go forward and see what's the needs from the industry and the government, and especially in our research and education. So here's the agenda. So we will focus apparently on a few of the topics listed on the left, and we will start with presentations from the speakers for 5 minutes of their research highlight. And then there might be some questions from the YouTube and the audience, and then we'll answer those. And then follow that, we'll have a panel discussion with some seed questions prepared. And finally, if we have time, then we'll do some open discussion from the chat. So then, yeah, let's just get started. Here's the research highlight.
Can I just say, Danning, I'd like to, again, thank you everybody for attending the session this morning. As Steve said, we're seeing across the board in almost every aspect of research, questions and an emphasis on the use of machine learning. Sometimes I think it's merited, sometimes it's not. And of course, whether this is fad or real is one of the challenge questions we'll throw out to the panelists in the audience. All of the panelists provided presentations that they recorded that you can find under, what do we call it? We call it a channel, or no, a playlist. So there's a playlist on the YouTube site for the CAV meeting that has all of the recorded presentations from panel members here. And I encourage you, if you haven't watched them already, to go in and watch them. They're very interesting. A lot of interesting research going on. And I think if you watch them as a whole, you'll see a lot of common themes among techniques that people are applying and the challenges that they're facing. And I will talk more about this in a few minutes when I speak, but we do see differences between the types of data that we work with and the challenges that we face in acoustics and vibration compared to some of the more well-known applications and success stories of AI and machine learning that we see in the press. So as Danning said, we're going to give a few minutes to each one of our panelists to talk about some of the highlights of the work that they're doing. Again, go watch the videos to see more details, and then we'll follow that up with some questions and answers among the panelists. And feel free to submit questions through the Q&A window in Zoom. We're also going to, as they say on TV and game shows, allow the listeners to play at home. So we'll have a series of poll questions that will come up during the roundtable, where we're encouraging you to provide your feedback and your input on these, and then we'll bring that back to the group as part of the roundtable discussion. So Danning, back over to you.
Yeah, sure. So then I have listed our panelists in alphabetical order, so we'll just get started. The first one is Gregory Banyan from Principal Engineering. And then I'll just, Banyan, do you have the slides?
Yes, hello, this is Greg. Yeah, I have my slides. Would you like me to present now?
I'll switch over to you. I'll stop my share.
Okay. All right, yeah, I'll turn on my video so you can see me and share my screen. Okay. Yeah. All right. So the presentation that I assembled for the CAV workshop, we just entitled a synopsis for what we're up to at Westinghouse with respect to machine learning, artificial intelligence, and what we're calling digital twins that are all focused on certain areas of commercial nuclear power. So in terms of the content that I included in the overall presentation, I broke that down into 3 different categories in which we're seeking to use this type of technology. First is that we're using these things to reduce the needs that we have in terms of physical testing and maintenance. So that has to do with not only at the operating power plants, but we're looking at the plants as well as in manufacturing facilities that we have. Secondly, we're looking at ways to better automate the analysis of data that we acquire during inspections. So there's, as you can imagine, a lot of inspections that occur throughout a nuclear facility, and oftentimes the analyses are quite burdensome as far as the engineering personnel requirements or even the computational expense. And so machine learning and AI have promised to alleviate some of those burdens. And thirdly, in kind of a general sense, we're looking at overall process optimization. How do we, minimize some objective function with respect to constraints that we have in a number of different settings. So in terms of today's discussion, I'll just jump ahead to a few topics that kind of all interrelate with one another and have maybe more of a strong tie to acoustics and vibrations than some of the others. So I'll briefly discuss Baffle former bolt predictions. I'll discuss neutron noise monitoring and component condition monitoring as far as the items here on the outline that I can address now. So skipping ahead. All right, so the first area I wanted to show by way of an example that could be illustrative to the CAV community here is what we call Baffle former bolt predictions. So these are bolts that surround the core. They hold together our core support structures. And due to the combination of irradiation, temperature, pressure, stress, and likely vibration, they experience irradiated assisted stress corrosion cracking. And that causes a certain proportion of the bolts to degrade over time. So here on my plot, we just have proportion of degraded bolts in the reactor plotted versus time. And the dots are showing different I guess, operating experience points that we have in terms of these bolts actually degrading at certain points in time whenever we go in and do an inspection. So in this situation, we used, to some extent, machine learning to mine the available data that we had from operating experience in conjunction with some metallurgical examinations, as is shown here from the SEM image, as well as some finite element methods, to develop what we termed a semi-empirical methodology with which we could predict the behavior of baffle former bolt degradation versus time, and subsequently inform when it's most warranted for plants to either purchase bolts to replace, do maintenance, and do inspections, and so on. So that's one area. The next area, which is related to that, still looking at the reactor structures, is how do we monitor these sorts of things in real time as the plant's operating. So whereas in the situation of baffle former bolt degradation, we're primarily just looking at the components every so often whenever an inspection is required. They'll go down with some sort of robotic device and examine via ultrasonics if a bolt's degraded or not. So contrast that with when the plant's actually operating, what can we actually see? And so there's neutron fluence detectors that reside outside of the pressure boundary of our reactor. And with those neutron fluence detectors, we can extract the oscillatory portion of that signal. And the oscillatory portion of the neutron fluence signal actually serves as a proxy for acceleration of many of the large structures that we have vibrating due to turbulence and acoustic-induced excitation. So right now we're in the process of using machine learning based methods in a few different settings so that we can more efficiently process the signals that we can acquire from these neutron noise sensors to basically do structural health monitoring. And in so doing, our objective is to enable the industry to move from more of a time-based paradigm for doing inspections and so on to more of a condition-based monitoring paradigm. The one thing I thought was maybe worth mentioning to the CAV is that we're in the process of looking at this with the existing fixed sensors, which are these neutron noise detectors in the context of a Westinghouse project. But the Department of Energy is funding some work that we're doing in conjunction with Wilkins Aquino at Duke University and Tim Walsh at Sandia, in which we're looking at complementing the signal acquisition with intelligent robotics, in which the robot would be moving around this region to potentially localize and more credibly identify damage. Part of how that work got going in the first place was I attended the CAV meeting, I don't know, maybe 5 years ago, and I met Tim at Sandia, and through that relationship with Tim, we spun up a little DOE project. And finally, just a way to kind of show how this could all fit into an optimization type of framework. We can look at some software that we're in the process of developing that we're simply calling component condition monitoring. And this development is meant to be, to some extent, component agnostic. But here you can just see a signal plotted versus time, and we're just using some regression-based machine learning methods to do anomaly. Sorry, my headset just disconnected randomly. Okay, so we're seeking to apply this to the features that we would be extracting from the dynamic signals that we're acquiring from the neutron noise sensors. So you can imagine that on this plot here, we're looking at something like the evolution of some dominant mode frequency or a narrowband root mean squared quantity across our spectrum, at a given mode of interest, and we're tracking that versus time. So this is an instance where we can use this software that's using regression-based machine learning to track. Sorry, my headset keeps disconnecting. I just got a new computer and my headset will randomly disconnect. So that's great. But yeah, in any case, the component condition monitoring program is the software architecture into which we'd be plugging in our structural health monitoring work for neutron noise monitoring that's focused on reactor internals. So by way of, I guess, kind of a brief overview of what we're up to, I thought that was maybe a fitting thing to share with the CAF. So I'll stop my screen share.
Thank you, Greg. Any question from the audience? Carl, do you have any question?
No.
Okay, then for the sake of time, let's move on to next person, Tyler Dare from Penn State. So Tyler, do you want to start the sharing?
Sure, let me
Yeah, I'll turn off mine.
just do this real quick. So I've been, I do experimental vibrations work, and I've, until somewhat recently, have been kind of professionally skeptical about how useful machine learning can be. And maybe it's because, I generally thought of machine learning as something that like Google's using to identify pictures, and is this a cat or is this a bird? And I didn't really see how that was going to be useful to someone who just measures stuff directly. Like I can just look at it and see if it's a cat or a bird, or I can use my oscilloscope and find out the frequency of something. I don't need a network to tell me what the answer is. I'm just going to measure it. So it wasn't always clear to me how this paradigm of going from like pictures to labels was going to be useful for acoustics research and experimental research in particular. And then on top of that, in my head, I'm thinking like, oh, I need some terabytes of training data, and I don't have that many graduate students, right? So I was a little skeptical on machine learning in general up until maybe a couple years ago. And part of the problem is a problem of terminology. This is on the screen is something from Steve Brunton and other folks at University of Washington, just different categories of machine learning, and they don't even use the term artificial intelligence. But there's a lot of people, when you say machine learning, just think of neural networks down here, or maybe some of these other things that start with deep. But there's a lot of other stuff that is really part of machine learning, and not just because people want to jump on the bandwagon and say, oh yeah, I'm already doing machine learning, but because we're already learning a lot from our data. So like putting a best fit line through a scatter plot is a form of machine learning. It's, in this categorization, it would be a supervised regression model, right? And maybe less fancy, like k-means clustering is a way of learning stuff from your data without knowing anything ahead of time. But since then, so I started out pretty skeptical, and I learned a little bit more, learned like the right things to Google, right? And I came up with kind of a proof of concept thing that here's a problem that I really couldn't solve without machine learning. At least we've been trying for many years to solve. So and there's more details about this in the longer video on YouTube, but I've got a panel, an aluminum panel. Actually, I have it right here. So it's 1/8 quarter of an inch thick or so, pretty thick panel. And this is an exercise in inverse modeling, so force reconstruction. So I take an instrumented hammer and I tap on the panel rings, I measure the response with some accelerometers. And the idea is, can I use the the measurement from the accelerometers to infer the forcing function. So this is, somewhere between really hard and impossible, depending on, the exact details of the measurement. On a panel, it's probably possible to do. But if the situation changes and you want to figure out what forcing function is caused by the turbulence going over your aircraft wing, like, good luck. It's really hard to do, and you can't always put sensors in intelligent places. So what I thought we'd do is let's see what neural networks can do in this case. And basically, a lot of the work in doing this was a lot of these neural network, the packages are kind of set up to work with images. You have to trick them into saying, oh yeah, this is an image, even though it's data from accelerometers. But in term the particular package I was using, I just said, oh yeah, I have a frequency by 8 image, and this is what these images look like. They're really just spectra, real and imaginary parts of spectra. But then we come to the problem of training data, because I'm not going to sit here and tap this panel all day. So what I did was made a finite element model of this panel, which usually you think, okay, I'm going to get really good at predicting the response of finite element models, and that's maybe not going to be, you can't extend it to real life. Well, if you put enough kind of fuzz on the finite element model and you say, okay, the mode, run it once to get some natural frequencies and mode shapes, and then say, okay, the natural frequencies are maybe like plus or minus 10% of that, and similar with like loss factors. So then you've generated this cloud of results from the forward problem, from going from the forcing function to the response. In real life, probably resides somewhere in that cloud. And you can think of the neural network I'm developing here as a really efficient way of doing this interpolation. It gets away from having to like worry about what the actual physics are involved, which is maybe kind of nice, and also maybe a little concerning. But this is like exactly the same kind of neural network that is sort of the hello world version that you would use to identify like digit recognition. Relatively straightforward convolutional neural network. And on the actual physical data, like that we took, hit every 300 points or something on here, the black circles here are the actual, the correct answer, and the red X's are where the network thinks you hit on there. It's not perfect, but it's pretty close, and it took way less work in terms of like expert development time that it would have to develop an actual model. And my network doesn't really care that it's a panel. It can be any kind of shape you want. And so the time to do the next one is that much faster. So that's sort of my brief journey from skeptic to believer of the usefulness of neural networks in acoustics.
Thanks, Tyler. Any questions or comments from the audience?
Yeah. Hi,
Yeah,
Gaurav here. Did you wish to address a particular technical problem, or this exercise was just to get a feeling for the possibilities of the
so this thing I kind of glossed over of figure out a complex forcing function on a vibrating structure is the actual problem, that shows up in lots of different places, and that's where the acoustics and vibrations part comes in. But all of this, this particular thing, I don't actually care where I hit on this panel. That's just kind of a toy problem. But the problem of what do you do, how do you pre-process the data, and how do you generate the training data is something that's going to keep coming up over and over.
Because you have mentioned the aircraft wing excited by turbulence. As an example, the difference being that in the aircraft case, you have a forcing function which is continuously spread over the surface, which has an infinite number of points, which is quite a large number. So
Yeah.
I wonder whether the same technique could be envisaged
Yeah.
ultimately.
Yeah. So I mean, the extension to that, which we have thought about, is maybe not so much pretend that I have an infinite number of forces, but I have some low dimensional representation of what the forcing function is, like a turbulent length scale, or you know, some, if I can model the turbulence with, say, fewer than a dozen parameters, if I can model the forcing function with not that many parameters, then we can attack it this way. So if you watch my video, one of the things that's mentioned is like neural networks are not a substitute for subject matter expertise. You need to know kind of what turbulent forcing functions smell like to be able to make intelligent decisions so your network can do its job.
Thank you.
Okay, that's really great. Although I do have another question, but I guess we need to continue for the sake of the time. So our next person is Yonghua Park from KAIST. Yonghua, do you want to start your slides?
Okay, so I will share my. Okay, can you see my presentation?
Yes.
Okay. So, okay, nice to meet you, and then good morning over there. So this is Professor Yonghua Park from Center for Noise and Vibration Control at KAIST, South Korea. So I supposed to introduce myself and my lab and my institute, something like that, but I just shortly saying show the chart. So we are 6 members, and we are very strong at the industrial application of sound and vibration in Korean industry, especially for the Samsungs and LGs and Hyundai's motor companies. So this is the research topic. So my laboratory name is the Human-Machine Interaction Lab by using the sound and vibration. So they are capturing the humans, the shape or the motion using the LiDAR or the vibration and acoustic recognition. For example, the detection of the human voice and human sounds. And I'm interested in also the inside of the human body, which is the application of the health sensors, for example, non-invasive glucose sensors, or the people identification using the vibration of the human body, which I will tell you shortly next. And this is the basic technology on the sound and vibration, which make all these application enable in the industrial application. So recently I developed a cough detection camera. Okay, so you know that we are very suffer from this COVID-19 situation. So we had a kind of the thermal camera in all the public the places to detect the fever, but we don't have a cough camera, okay, in the public place. So this is my the motivation of this research. So I'm now developing this kind of a cough detection camera. So which have about the 100 microphone, okay, over this, and then it can detect the direction of arrival of some sound, and then it has a camera over there. So by mapping this direction and the camera, we can visualize the source of the sound. And then I want to combine this the sound visualization with the cough detection by using the neural net, in this case the CNN. So as we did, we select the CNN for this type of application because the spectrogram or the Mel's frequency spectrogram is very nice to have the good result for the sound classification. So it turned out that, so we choose the CNN among these the AI algorithms. And the feature is the very important to determine the performance. We examine the time profile as well as a Mel scale spectrogram or the MFCs, the many of types. But it turned out that the Mel scale spectrogram is most effective to detect the human voice sound because you know that it has a kind of the abstracted the information by the biomimicking the human hearing system, as well as some kind of the full of the physical properties inside of this spectrogram. So we intensively use that, and then this is a CNN. This is not particular CNN, but we optimized many of the hyperparameters. And then at the first step, we choose the publicly open the cough sound, which comes from the audio set. And then it has many of the human sounds, including the noises. And then we select cough sound from here. For example, some cough, and then the noises. Noise is also very important. But it turned out that the data is not enough, not always enough. Okay, I can guarantee that. So we augment data by using the combination or some time shift or frequency shift, and even we did some synthetic data by using okay, this kind of the reverberation sound generation, and that reverberation sound is generated from the impulse response function, which is related to our application room, for example, hospital room, things like that. So we increase the chance of the accuracy of our algorithm. Okay. So as a result, we have about the 80% the accuracy in the application when when it is tested in the real office room. So here is my demonstration video. Okay, do this. So I cough, and then this is the visualization of the cough sound. So we can identify who are coughing. So my first application will be in the hospital, by the way. Okay. So I will, and I will.
I think we need to try to keep the time tight.
Okay.
Yeah. So
I will finish my presentation in 30 seconds. So this is a personal identification. So by using this is a biometric the identification using the vibration of the user's fingers, so that we can use this vibration to open our the cell phone. So we did some rigorous analysis on the biodynamics, and we did the vibration test for the human fingers. And as a result, we can there are some the intermediate process, for example, cancellation of the sensor effect, or the choose the optimum frequency band. And as a result, we obtain this kind of a very accurate the result for the human the identification by using the fingers. Okay, so this is a preliminary result from me. Okay, thank you.
Thank you, Yonghua. Any questions from the audience?
Yes, Goran Pavic. Your work seems to be very interesting, really. Now you are at the step of identifying cough as a
Yes.
source of sound. Do you think that using, by extending the technique which you have started to develop, even different types of coughs could be recognized by a machine, or this is an illusion? I would say if, for example, a particular disease like COVID-19 would have a particular signature of the cough, as compared to other types of cough which may be caused by other reasons, not by COVID. Do you think that one could imagine, not now, but in some future, to go even further and be able not only to recognize the person who is coughing, but to recognize or to try to categorize the cough as a bad one or a friendly one?
Okay, Goran, that's a very nice question. The answer is very simple. If the human can distinguish that the true cough from the COVID-19 or the other symptom, then the machine can distinguish that. Okay, so this is the answer,
Right.
which means that if we have the physical kind of some difference between the two, then we can definitely we should model. We should train this data by collecting that data. Okay, but theoretically possible. But I think that it is practically very difficult, because the cough sound itself is very difficult to distinguish due to its the causes.
Right.
So this is my general answer.
Right. Thank you.
Okay, that's a great presentation. I especially like the application in the coughs. Now we need to switch to the next person.
Okay, thank you.
So first stop the sharing and turn on the new share. Yeah, I think I kind of my slides got shuffled. The next person should be Eric Greenwood, my colleague from aerospace engineering. Eric, do you want to share your slides?
Yeah, sure thing. Thank you.
Yeah, I'll turn off my share.
Okay, hopefully you got my slides up there. So great, good. Yeah, so my talk, this is actually has a similar theme to what Tyler had talked about. So my work's in rotor aeroacoustics, and the big problem here is there's never enough data. You know, I'm trying to figure out ways we can use this data to do more varied and useful things. And then the genesis from this is really from kind of my previous position. I was at NASA Langley running the acoustic flight test there for helicopters. And we were able to show, at least for a specific helicopter at a specific configuration in a specific place, right, we could really effectively reduce the annoying noise that was being, sent to people on the ground through controlling the helicopter's operations. And then that's largely because, the main source of annoying noise, at least when it occurs, is the interaction of the rotor with its own wake. So we call it blade vortex interaction. Up here is like a little notional diagram that kind of shows some guidance you might give a helicopter pilot about, what, say, sync rates and airspeeds you should avoid during an approach or some other operation to avoid creating this annoying noise. Now, as we collected more and more data, or say the last decade, we realized that the problem was a lot more complicated as we thought, unfortunately. And so the behavior of this kind of diagram and the operational guidance you should give to pilots changes a lot depending on the current weather, the configuration of the vehicle, the particular type of vehicle that you have. And collecting this data is really, really expensive. So there's just no way we could possibly characterize everyone's helicopter for them, especially under every condition they might fly it. So we were looking for another way to do this. So here's some plots of some of the measured data, and the main point here for different helicopters is to kind of show the region of the operating envelope that's noisy changes a lot depending on the helicopter that you have. So, guidance we might develop for a light helicopter like a Robinson R44 is probably not that great for even slightly heavier helicopter like a Bell 430. So the trick here, being good engineers, is to apply some subject matter expertise to make up for the fact that we just don't have billions of data points. And one of the ways, of course, we can generalize our data is just to go back to Buckingham Pi theorem and try to non-dimensionalize the problem. And there's a set of non-dimensional parameters for the rotor aerodynamics problem that work quite well for acoustics as well, because we're worried about this interaction between the rotor blades and the wake. So we're going to try first just to non-dimensionalize everything. And in combination with that non-dimensionalization, and this I go into more in my talk, but we can apply some additional heuristics and use some machine techniques to kind of overweight and oversample their data to make up for the fact that we don't have much of it. And then come up with actually some fairly effective models. We're operating on this non-dimensional basis that can identify the likelihood that a region of the vehicle's operating envelope is going to be a noisy region or a quiet region. And then this just shows this model being applied to a helicopter that it's never seen before, and trying to estimate where these red dots are that are the noisy region of the operating envelope. And there's a lot of different machine learning techniques that can do fairly well on this problem. And to give you some example now of the kind of the results that we could generate for pilots based on sort of the dimensional terms, so rate of climb and speed that they'd be used to seeing. Here's kind of outputs where we have identified the noisy region for, again, a set of 3 helicopters spanning from some of the lightest ones that we measure, like an R66, to some of the heaviest vehicles that we can measure. So like a MIL Mi-17 or Mi-8. And you can see, even though these noisy regions have fairly varied properties, we can do a pretty good job identifying them. If we're careful and apply some physics to the problem in addition to just machine learning. Sometimes you want more detail, and that's kind of was the second part of my talk, where we started talking about trying to inform an analytical model that we might have of the helicopter noise sources. In this case, they're both the acoustics and aerodynamics, using some measured data as basically a parameter identification process. So I described a parameter identification process I came up with called FRAME, where essentially we're taking an acoustic signal. So this is something, a non-dimensionalized blade vortex interaction pulse, and then essentially running an optimization problem where we try to adjust the input, the calibration parameters in our model until we're getting the same output in the time domain as we were in our measured data. And we want to try to extract as much information as we possibly can from the limited data that we have, which is part of why this is running in the time domain. We're hoping, if I can get the phase relationships of this impulsive source of noise correct, then I hopefully am modeling the physics fairly well. Even though maybe what I care about is something like a weighted sound pressure level. I want to exploit the fact that I have this information in the first place in tuning. And, again, by doing that, we can do a fairly good job. So this shows these are now noise spheres. So if we assume the vehicle's a compact source, this is basically a weighted sound pressure level as a function of directivity angle. So over here on the left is, sea level measured noise. And this red hot spot that you see is the blade vortex interaction noise. We did a flight test where we repeated the same measurement with a helicopter at 7,000 foot above sea level elevation, and the intensity and directionality of that noise changed. And when we calibrated our model using the sea level data, this FRAME model, we could indeed show the same change in that blade vortex interaction noise level and directivity fairly well. So we were capturing the physics. And that lets us do some kind of neat stuff because this model is still fairly lightweight compared to a heavier prediction tool, where, for instance, we can, this is somebody I did with my colleague Anna Trujillo at Langley, we can show a helicopter pilot what the current noise footprint is in real time. even faster than real time to do some kind of prognostic planning. And then hopefully the pilot can try to keep this noise footprint away from areas where you might have noise sensitive communities and so on. So that's basically the quick summary. Thanks.
Thanks, Eric. Any questions from the audience or comments?
Derek, this is Steve Hambrick. One thing that struck me in the talk, which is great, by the way, is that you said you at some point you had to seed some extra kind of bogus points in there because there was an inherent bias in the neural network or the machine learning, which is new to me. I don't know if you could expand on that a little bit.
Yeah, so like a lot of these machine learning algorithms tend to be biased towards, especially in a classification problem where I'm trying to figure out, in my case, noisy points from not noisy points. They'll tend to be biased toward whatever category you have the most data points of. So if you're like, I have a problem where I have 7 not noisy points for every 1 noisy point, so they're heavily unbalanced. So the results are not going to be great if I just apply it naively to that data. If I'm a big data problem on Google or Facebook, you know, my solution might just be to remove points from the overweighted data set until they balance out. When you don't have a lot of data, though, you don't have that option. So you can do things like count every point that you have multiple times, but that kind of builds in some of the structure of the data that you did manage to sample. And again, if it's a flight test, that's pretty randomly distributed into the problem. I talked about a technique I use that's good when you have really little data, where you actually kind of try to identify the region where this area is happening and then quasi-randomly add more synthetic points to balance them out. But there's lots of ways to do this. It really depends on your problem, what's going to work well.
Okay, so
Eric, this is Carl. You had in your video, you talked about using several different machine learning techniques relative to this problem of seeding the data to try to get a balance between the different classes. Did you find that one of those techniques was more sensitive or less sensitive to how you tried to balance out the class populations?
Yeah, and I think there are some fairly well-known things. Like we did some stuff with like a random forest analysis. I think that is not actually very sensitive to overweighting, right? Where you had like a decision tree and you're trying to figure out what parameters matter. Something else like the support vector machine type classifier is more sensitive. So I think a lot. I didn't look too thoroughly at which ones are the most sensitive ones. I found a process that worked to balance out the data. I pretty much used it everywhere. But yeah, some of the decision tree based classifiers are not really sensitive.
All right, thank you. Next up, we have Mehrdad Madhavi from Penn State University. Mehrdad?
I think we have you on mute still.
We're good.
yes.
So I just said that nice to meet you all, and it's exciting that see how machine learning being used in many different areas. It's very exciting, but I'm gonna switch the gears. So my research is on fundamental aspects of machine learning, and I run the machine learning and optimization lab at computer science department. So today I'm just gonna give overview of what we do. So basically, based on my experience, I see a danger for machine learning, which is seeing it as a perfect black box tool that can be used for knowledge discovery or different applications. And what we do in our lab is basically trying to open this black box and see what's going on and develop algorithms, efficient algorithms with provable guarantees. So what are the things basically we look at when machine learning is going to work, or for a given problem, what's the best algorithm that we can have that also has some provable guarantees? For example, large scale machine learning, distributed optimization, how we can mitigate bias and have fair algorithms, how we can protect against malicious attacks, have robust algorithms, adaptive learning, and then I also mentioned some new research directions that I'm exploring now, which might be interest of this group. So one of the aspects that we focus is optimization theory. Basically, with this availability of this all packages, PyTorch, TensorFlow, it's now easy to go just run and tune the parameters and get some results. But it's kind of dragons training this over parameterized model, which means the number of parameters usually goes beyond the number of training examples. It's really hard. It might take weeks, and with hyperparameter, it might take months. And this is very scary optimization problem, which basically needs to be tackled. So one of our focuses developing efficient algorithms that works well. And one thing that we care is the goal of machine learning is just not optimization, it's generalization. We want to have algorithm that works on the unseen test data. So here I'm just showing a landscape of typical deep neural network. You can see it's highly non-convex. So the question is which optimal local or saddle point my algorithm is going to converge. Can I say anything about the convergence, about the generalization? Or can I help my optimization algorithm to converge to a global minimum and escape saddle points? So these are basically some aspects and problems that we look in our lab to solve. And one thing is basically with the rise of deep neural networks, all the theory we had in classical learning theory phase. For example, I give you an example here that basically Eric talked about SVM, random forest. We have different models, and on the left-hand side here, I'm showing you the figure A. This is the classical viewpoint of machine learning. As you make model more complex, for example, using more trees in decision trees or adding depths to decision trees, the training error goes to 0 and test error reduces. At some point it starts going up, and this is the sweet spot we usually try to find by hyperparameter optimization. On the left-hand side, I'm showing you what happens in deep neural networks. We still see this U shape, but if you continue training the deep neural network, you'll see that the test error starts decreasing. So if you just do this apple-to-apple comparison to the classical viewpoint and what we observed in reality, we see that basically deep neural networks contrast this classical viewpoint. So understanding this phenomena, why this happens, how it's related to optimization, these are challenging questions that we try to answer. And there are many other aspects that phase that for brevity I skipped here. We also work on randomized algorithm. For example, imagine a deep neural network with billions of parameters, and we deploy it in our cell phone. Now we give a data, we want to evaluate it. So if you want to make real-time decision, it's going to take seconds, which is not favorable. So the question is, can we accelerate inference, for example, by quantizing deep neural network? If so, what's the right way to compress or quantize deep neural network so we can accelerate the inference? Another aspect is basic distributed optimization, that usually it's hard to gather data into a central server. So we try to do distributed optimization for machine learning, and the goal is obviously to reduce the communication because it's bottleneck. Also, the size of messages that has been transferred between different machines. For example, if you have 10 to power 30 parameters, which is a typical number of parameters in ResNet and state-of-the-art deep neural networks, it's really time-consuming. So these are the aspects that we try to come up with efficient algorithms and also prove convergence rate. And more recently, federated learning. So this is kind of distributed optimization but motivated by edge computing. So there are 3 billion mobile phones that they keep generating data, which is good. But unfortunately or fortunately, the privacy issue doesn't allow that we have access to their data. So the question is, can we basically learn a model without accessing the raw data? So this is basically, I think it's the next generation of machine learning in healthcare, education, and some other applications that we try to bring machine learning on edge devices and preserve the privacy of the data. And on the application side, I also work with Nikolai at Hershey Medicine School on drug discovery. So one of the problems that we work is, which I learned a lot actually, is protein ligand basically docking for drug discovery. And here the search space is exponentially large, and really it's really hard to train. So we come up with machine learning on first how to evaluate the docking, and also how can we use a smart reinforcement learning type of algorithm to efficiently search the solution space. And basically this new collaboration with on drug discovery basically brings me to this recent agenda that I'm working is machine learning for knowledge discovery. So which might be relevant to this roundtable. Basically, any scientific discovery basically goes through this life cycle. We start with some question, we hypothesize, we try to evaluate it with observational experiment, then we refine our hypothesis, and we keep doing this. So my understanding is machine learning is good at some aspects of this, and we're still missing a lot of pieces in the life cycle of knowledge discovery. So that's basically, we're trying to have a center here, basically to go beyond just prediction and training and try to see if we can complete this life cycle. So some of the aspects I'm looking for now is self-supervised learning, or learning from small data. For example, in drug discovery, it's really hard to go out there and do lab experiment because it takes time and expensive. How can we learn from small data? Can we do self-supervised learning? Also, this examples that you show, for example, can we use machine learning for robust control problems? Mitigating bias that Eric talked, for example, imbalance data, that I have a PhD student that his thesis on basically this whole problem. Interpreter models, I think we need this to bring the domain knowledge to machine learning. Safe and robust machine learning. Yes, in image discovery, this kind of toy applications, it's okay if we make mistake. But when we go to the control problems or the problems that we discussed now, it's really important to not to make mistake and make sure our algorithm is safe and robust. And I think the ugly part of machine learning is this hyperparameter optimization, how to tune the learning rate, which architecture we pick. All these questions, I think, takes 80% of the time to do research in machine learning. So we're trying to come up with some auto ML or automatic machine learning, trying to automate this whole model selection. For example, should I use SVM, decision trees, deep neural network, this kind of things. So if we can automate it, we can help the training basically. So I just wanted to give an overview. I know it's a little bit deviates from the other talks, but I would be happy to take any questions if you have.
Thank you, Mehrdad. Do we have any questions from anyone?
Hey, hello, this is Daniel. I have a quick question.
Sure.
And I'm sorry for my lack of knowledge in machine learning, but I'm currently designing resonators using optimization. So currently I'm using a gradient-based method, which requires an analytical derivation of the problem.
Mm-hmm.
So because of the complexity, I am considering to move to genetic algorithms, but I see that machine learning could be an option. The problem is that I have a lot of variables. I have thousands of variables. So my question is, will you recommend me to explore machine learning instead of genetic algorithms, for example?
So yeah, basically learning to learn, what would be one thing that you can explore, or even if you don't have access to analytical function to take gradient or whatever, you can use zero-order optimization that you only have access to function evaluation. But you have to guide the search process, which points you want to ask to be evaluated to make it fast. So this is beyond the scope of this roundtable, but you can, if you can email me, we can have a Zoom meeting and discuss details. But I'm sure you can do, yes.
Oh, perfect. Thank you. Thank you.
May I ask a question? This is Goran Pavic. One of your last comments was about the possibilities of automated machine learning and automated model selection. Could you be just a little bit more specific? How far this idea has gone? Is it just a theoretical concept, or because I'm not good in the field, you see? So could you?
Yes, correct. This is one of the key challenges for machine learning. I mean, you ask question that you evaluated SVM decision trees, which ones works better? The point is there is no single model that works best for all data. And even for a single model, we have tons of hyperparameters, learning rate, the architecture, and even we go to deep neural networks, there are some tweaks, batch normalization, number of hidden layers, or loss function. These are all needs to be handled manually. Unfortunately, at this moment, we don't have any universal recipe or algorithm that covers all this. But we can develop algorithms to do this. For example, for hyperparameter tuning, we can develop algorithms that efficiently tune the parameters for us with reduced amount of human involvement. But it's active research. It's one of the challenging and open problems in machine learning. But yeah, there are some recent progress. For example, Bayesian optimization to automate some of these processes rather than manually tuning the parameters, for example. Or architecture search without network architecture search. Can we learn the best architecture without just trial and error on different architectures, basically? That becomes a different learning problem.
All right, thank you, Mehrdad, and thank you for the questions. Next up, we have Montana Morris from local company here in State College, KCF Technologies.
Hey, yeah. Thanks, Carl. I'm really excited to be here. I gotta say, before I even dig in, just having sat here for the last hour, I'm so grateful to be having these conversations. The work that's going on in this field it's really fascinating to me. I gotta admit. So my presentation, let me know if it's coming through, by the way. Oops. New share. I think it should be screen 3. We'll find out. Let me know if you guys got it.
Yep, we can see.
Yes.
Perfect. Thank you. So my presentation was centered around actually a couple of different deep learning frameworks that we're looking at researching at KCF, and we've these are really in the incubator phase. Think, something that really I think will have an impact over the next 5-10 years. And the two concepts were reinforcement learning. So you think about, we talked about controls problems earlier. I know that one of the guys had mentioned it. And reinforcement learning are sets of algorithms that allow these agents to learn the optimal controls or the optimal policy for a given environment. And then the difficulty in industry is that in order for a reinforcement learning problem to be solved or to be optimized, you need some type of environment for that agent to learn in. And for that, I'm proposing that we could use generative methods like GANs to actually provide the environment for that agent to learn in. So this is kind of a futuristic, forward-looking conceptual overview. We are doing at KCF some more grounded things in production. I know that Eric mentioned earlier about synthetic data generation. We use a technique called SMOTE. It's like kind of the standard for that quasi-random data generation that he had mentioned. We use a lot of like robust feature engineering. So you think about if you have, you know, a washer that's imbalanced, meaning like your washer in your house, you know, that consistent 1 times the running speed that you'd hear from your washer, that same type of behavior comes into industrial equipment. So we are using more standard, I would say, less deep techniques to actually provide value in production today. But this exploration is something that we'd like to get into in, you know, the next 3 to 5 years. So I'll try to dig in and keep it brief. For folks who aren't as familiar with machine learning, some of the concepts are probably going to be a bit dense, but I'll see what I can do in 5 minutes. I'm going to skip through here. So basically, the first piece that I framed up in the presentation is that your controls problem, at least from a machine health perspective, is really about minimizing vibration, subject to keeping your product quality and volume constant. So if you're in a manufacturing facility, you want to make sure that you have, you know, let's say it's 10 goods coming off the line every hour and they all have perfect quality control. Let's say that that's the constant. And if you wanted to use machine learning to minimize your machine health or your machine wear, you would be trying to minimize the vibration in some sense. There's some nuances to that in terms of which specific parts of the vibration spectrum and how does that actually cause machine wear, but that's a different discussion. And the idea is that we're trying to train some type of model to be able in real time to make those decisions. So pull those control levers such that the vibration is minimized across this factory while keeping the production volume constant. So that's kind of the problem that we'd be looking to solve in most manufacturing facilities, at least from KCF's perspective as a machine health organization. So I propose that we could use reinforcement learning to solve that problem. It's a kind of a textbook control problem, a control optimization problem, where you have some agent, which is essentially the equivalent of your pump operator, let's say, it's making decisions about the controls in such a way that minimizes vibration. But the question becomes, like I had mentioned, how do you actually train that agent? Skip ahead here. And what I'm proposing is that we could use generative adversarial networks, which is a neural network architecture that was relatively recent. In 2014, a paper came out from, I think it was, the guy's name was Ian Goodfellow. I think it was out of one of the Google DeepMind labs. But basically the concept of these generative adversarial networks is that you have 2 networks that compete in a zero-sum game. And the idea is that there is this generative network that is trying to fool a discriminator network that its synthetic data points are real.
Hey, Montana,
yeah.
should we be seeing the slides changing?
Yeah, you should be. Are they not coming across?
It's not happening.
Gotcha. Thanks, Gary. Let me know which, let's see what happens here. How about this? Is it changing now, Gary?
Not yet.
Interesting. Let me try again.
You want to close the share and share again?
Yeah, let me try. Let's do that.
There, you got it.
Perfect. It jumped now?
Yep.
Yes.
Got it.
Okay, thanks for that. I probably missed a few slides. I'm going to dive in anyway, just for the sake of time. But the concept that we got to here is that there is some machine operator, but in this case, an algorithm that is trying to make decisions in some environment to maximize the machine health for this manufacturing facility. And there's these generative networks that would be able to essentially create that simulated environment for this agent to learn in, is kind of what I'm proposing here. So in these settings, this generative network right here, let me know if you can see a pointer. This generative network takes in essentially from a random latent variable space. So you have this kind of open-ended probability distribution that would go into this generative network, and it transforms that latent space into some synthetic data point. And what happens is there's this discriminative network. So we basically took an unsupervised learning problem, which means we're just trying to essentially model data so that we can have a synthetic environment. And we turned it into a supervised learning problem because we have real responses, which are labeled as real, and synthetic responses, which are labeled as synthetic. And the discriminative network is trying to say, is this a 0 or a 1? Is this real or is it fake? So we've essentially created a supervised learning problem from an unsupervised learning problem. So the idea would be that we can take this generative network by competing it against this discriminative network in this zero-sum game, trying to avoid some of the math behind it. But basically, these two networks compete until the discriminative network, kind of when this problem is optimized, when it's solved, it just guesses 50% of the time it's real and 50% of the time it's synthetic. That's kind of the solution of this system. The synthetic generator has been able to create responses that are indifferentiable from the real responses. So once again, there's a training technique that uses kind of a stochastic gradient descent where it optimizes the different responses subject to that loss function. And what you end up with is this environment at the end where the real vibration and the synthetic vibration are nearly identical given to a specific environment. How am I on time? About another minute here. And the idea is that once you have that synthetic environment, you have a space for this reinforcement learning agent to go in and then learn the parameters that it should take or make in a given environment. So like if we have a set of pumps that are in line, it should be able to have a digital twin, like Greg said earlier, but a digital twin that doesn't exist in reality. It can go out and learn that I should have these two pumps in third gear and this pump in fourth gear. And then when you deploy that model in reality, it would have that set of parameters that has now been tuned so it knows what decision it needs to make. And we can kind of, if anybody has questions, I'll open it up at this point for questions. Like I said, it's pretty dense for some folks who aren't quite as familiar with these specific deep learning kind of problems, but it's definitely exciting. And I think it's going to have a big impact here relatively soon.
Okay. Montana, thank you very much for your presentation. I think given that we're kind of running long here, I'd like to give Goran a few minutes to just briefly summarize his work, and then Denning and I will forego our time so that we can get to the Q&A. So maybe we'll come back to some questions for you on the GAN approach as part of the general Q&A.
Awesome. Yeah, I appreciate that.
Thank you. Goran, if you can give us just a minute or two summary of your work, and then we'll move on to our discussions.
All right. Sorry, I have the same type of problem as I did yesterday.
We were seeing your screen.
Yeah, I know, but
Gordon, we're happy with half the screen there. That's fine.
Yeah, that's fine, Gordon.
Yeah.
Yeah, but for some reason I can't control the PowerPoint. But never mind. This is life, I suppose. So I was going to present a layman's way of addressing monitoring of pipes by using some so-called smart techniques. We are faced with the problem when we have pipes that the pipe motion can be quite complex, and we can represent it as superposition of different waves, some propagating, some evanescent. And the starting position here to this approach I'll be talking about is that we have a model of coupled fluid wall motion of a pipe. The model is quite complex and it provides multi-valued analytical solutions. Important thing is that it is analytical, not numerical, and each solution represents one particular wave. So what we can get from the model is the wave numbers for each wave, axial and radial, the ratio between the motions of the pipe wall, because we can split it into 3 orthogonal components, and also what is very important, the ratio between the pressure in the pipe and the wall motion. And all these parameters depend on frequency and on pipe parameters. The idea is that we make a sufficiently clever combination between measurements in several points. So this would be normally a multi-point measurement between the possibilities which we have with this generic model and with some data processing to extract from all of these 3 components the required parameter which is of interest for the monitoring. For example, we can look at how the thickness of the pipe evolves in function of time, and therefore survey the corrosion or erosion of the pipe wall, which is not seen from the outside, for example. Now, it turns out that there are 3 wave types very suitable for the analysis, because these type of waves propagate at all frequencies, contrary to other types of waves which are at low frequencies evanescent and which start to propagate only at high frequencies. Now, we have, I'll switch off these. I'm sorry. We have, we may have presence of gas and impurities in the fluid. These will change normally the bulk modulus and perhaps to a certain extent the density of the fluid. We can have abrasion, corrosion, and some effect which would reduce effective thickness of the pipe. Now, if we, for example, know what is the sound speed in the fluid, we can then infer the bulk modulus, and then by knowing the sound speed in the fluid, we can see whether something is wrong with the fluid inside, whether it's getting, for example, some gas in it, etc. What we can measure on this in the pipe is the wave speed. And the wave speed is not the speed of sound. It is affected by the impedance of the wall. It is different. And it depends on the sound speed and on the thickness. So as a result, we can identify the sound speed, which will tell us about the state of the fluid, and the thickness, which will tell us about the state of the pipe wall, and even reconstruct pipe dynamics. That means measuring on one part of the pipe, we can reconstruct the dynamic quantities elsewhere, since our model provides for that. Now, the challenges we are facing is that in order that our measurement with which we feed the model are meaningful, we have to have a very good matching between sensors. And on the other side, since the model involves some fairly complex mathematical procedures which are not simple to use by an end user, by a typical end user for industry, we have to develop an approach which will deliver the required technology to end user. So these are problems which are normally not very popular in academic world, but which are real world problems. So the strategy finally is develop a friendly technology transfer to end user using a particular technique of parameter identification, identify the parameter which you are interested in for monitoring, like thickness or like fluid state, single parameter or several of these parameters, and also make something about autocorrection for measurement, for possible measurement imperfections. I'm now very sorry about this, and I still don't know how. Oh, sorry. I now seem to be able to control my PPT. So here are some examples. Out of measurement in several points, by using auto and cross spectra, we can construct a so-called cost function, which is a function of unknown speed, wave speed in the pipe, and the position of the maximum of this cost function will tell us about the actual wave speed in the pipe. So this wave speed we can then put in the model in order to obtain a required parameter which we are looking for, like a sound speed in the fluid or like a thickness, for example. We can also make a two-dimensional parameter analysis by taking as unknown parameters sound speed in the fluid and flow velocity, if we don't know what is the flow velocity, and again construct a particular cost function, again such that its maximum will reveal the actual sound speed in the fluid and actual flow velocity. This is the result obtained on measurement on a compressor, air compressor pipe with, I think it was 50 bars, and don't know the temperature was not very high, and it was 30 degrees, I believe. And finally, by making measurement on one part of the pipe, we can retro-propagate this to another part and obtain, as in this case, for example, the spectrum of pressure pulsations in a particular point, in any point on the pipe, and or the spectrum of stresses in the pipe. Here you see the measured and reconstructed spectra. They are practically identical, and here we see the zoom of this section, which shows the differences between the two. So very good matching can be obtained in this way. Now, for correcting for sensor sensitivity, if we take pulsating wave, and I'm here presenting just the pulsating wave, although other types of waves can be used for monitoring, then we can use a sensor which is a strain sensor, actually a piezo wire wound around the pipe. We can use such a sensor in several positions, and it may turn out that since the simplest way to put the sensor is to apply by hand a tensioning force, then the sensitivity of different sensors we put in an array are not identical, and we don't know what are the sensitivities. So there is a way of even not knowing the sensitivities, which are critical for a correct reconstruction of the quantities, we can correct the unknown sensitivities and obtain correct results. So here a cost function, two-dimensional, unknown sound speed, and unknown ratio of the sensitivities of 2 out of 3 sensors, which shows then when the sensitivities are correct ones, which indicate by number 1 here, we get the maximum at 1351 meters per second, which is the speed of the sound in the pipe. When we have sensitivities which are not matched, we get the maximum not at the position of 1, but of the position of actual ratio of the sensitivities, but the speed is nevertheless the correct one. So one of the major difficulties in practical measurements, when the sensitivities of different sensors are not identical and unknown to us perfectly, can be resolved by the applications of these particular cost functions, which then represent in a way a smart pipe analysis. And finally, this is the last slide, how to transfer the pipe model, which is required in the whole monitoring story, how to transfer it to an end user, take into account that the model is fairly complex. So the solution we have is to create a pipe database where instead of having input data as most of databases have, we have inside pre-computed results already ready for use in a very condensed form, in a zipped form. And this is done owing to the reformulation of the model of pipe in a non-dimensional way, which allows for an extreme compacting of results in for a small number of data. You can cover a huge number of pipe cases. The end user have then to select in this particular procedure the pipe case, for example, steel pipe and water as fluid, and thickness to diameter ratio of his pipe, and then get the coefficients which correspond to this pipe case from the database. And since the database will not have the thickness to diameter ratio, perhaps, which is exactly the end user's value, the linear interpolation was shown to satisfy well the accuracy. And then finally, the end user can reconstruct the targeted quantity by polynomial expansion, very simple to do. All what he needs to do is to specify his frequencies, and he will have his function obtained readily from the database. So this is simple on end user side, a little bit more difficult on our side who provide databases, but end user doesn't care about it. One example showing the accuracy of this zipping and unzipping using polynomial approximation of the required function used in the monitoring process. This shows that error in data zipping is rather small, definitely acceptable for in-field applications. So this is my last page, which shows that we should make everything to make our pipes great again. Thank you for your attention.
Thank you very much, Goran. And thank you to all of our panel members for their videos and their presentations. As I mentioned earlier, please go watch the videos if you haven't done so already. There's a lot of really great information in those beyond what the presenters gave this morning. All right, at this point, we'd like to, we've kind of seeded the discussion with a couple of questions for the panel members. And I will turn it over to Danning to introduce the first one.
Right, yeah, so yeah, and here, let's see. Yeah, please use the chat function in the Zoom to raise questions, and then we'll start with the first one. Somehow, wait. I think I'm having a technical issue here. Oh, okay, there we go. Okay, yeah, the first question, I believe Kelly has prepared a Zoom poll asking like whether machine learning is a fad or real trend. To explain that, oh yeah, here's, oops. Do we get any results from the poll?
Yeah, it's just showing up, I think, for us hosts. So far, nobody has voted for fad, and 19 people have voted for trend.
Okay, somehow that's expected. Yeah, so here we are showing this Gartner hype cycle, which you probably have seen for a lot of applications. This is the latest one that I can find from last year. And there are some emerging technologies, and probably half of them are about AI and machine learning. And actually here are a lot of specific fields of AI, like explainable AI and AI as a platform of a service and things like those. Since they are all in this innovation trigger and the peak of inflated expectations, but I guess this would depend on the field. Maybe in, okay, so we get the result. Everyone said it's a trend. That's amazing. Okay, so but then it will be interesting to see from the panelists on like what do you think, whether it's a final trend in the field of vibration and acoustics. So which one, who want to start?
Hi, this is Lee Tito. I just want to say I think maybe a more important question is how utilized this capability will be. When you say fad or trend, I mean, it's almost like it doesn't work or it can work. And I think most people acknowledge that there are some applications where, it has some utility, but, how prevalent and how much of a machine, if you talk about machine diagnostics, okay, trend, how much would the AI part be used in machine diagnostics as opposed to more physics-based or traditional type of diagnostics?
Yeah, that's a great point. Actually, our next question would be more specific to the challenges in the acoustic and vibration, like what works and what didn't work. And here we are mainly first work on a bigger picture of this trend of machine learning. So Steve, do you have any comments on this curve?
Oh, it's just one of my all-time favorite curves. It just seems like anytime there's some new hot topic that pops up, there's all this funding that gets poured into it, especially in academia, right?
Mm-hmm.
And you go to conferences and half the damn conference is like working in this one topic area. I can think of a couple of hot topics that I will mention here, but within a few years, all of a sudden that crowd is diminished and they're all into something else. And so we're starting to see the beginning of all this in our technical conferences now with AI and machine learning sessions, and everybody's pouring themselves into it. Is this going to carry on, or is it going to have that same trough of disillusionment as we go forward? Time will tell. We really have no idea, but it's great to get perspectives like what Lee had from industry. It's like, what pieces of this might work and how can we apply them?
Mm-hmm, right. So maybe
I think AI and ML is a particularly interesting area when you look at it on this kind of hype curve, because 5 years ago, if you were to draw this hype curve for AI, it would have been shifted to the left. And I think that we would see that we were on that kind of slope of enlightenment, plateau of productivity at the time, because neural networks have been around, well, specifically, I guess, neural networks have been around for many, many years. And there was a lot of promise, there was a lot of hype. And then we found that there were just problems that couldn't really be solved with neural networks at the time. And then as we saw the development of things like deep neural networks, and particularly applications to things like image recognition, then we started to see a lot of applications building. And now we're kind of in the next wave of the hype cycle here. Mm-hmm. I think that one thing that is important to think about is the distinction between AI, artificial intelligence applications, and the applications of machine learning, which personally I see more as a tool set. Mm-hmm. And to see if we're going to find that, you know, there's a bunch of problems out there that we are trying to apply this to, mm-hmm. that it just doesn't really work that well for, and might kick us down into that next trough before we get the next wave.
Yeah. Hey, Carl, if I could pipe in here, this is Gary Koopman. You know, along fitting in here is the I guess the trend towards the excitement about big data mining, that if we could apply these methods to big data, that we would be able to come up with all kinds of predictive models for health or machines or whatever. And that big data kind of went by the wayside as well. I don't hear much about it anymore, but I think it fits in here.
Right. Yeah. That probably.
Yeah. Thanks, Gary.
Mm-hmm.
And one other thing I just want to say, in the acoustics and vibration realm, with resonances and machine issues being at resonances, trying to correct out with a model-based inclusion is tough, in that the only way you can do it is almost be spot on, exact on the natural frequency. I mean, you have the sharp gradients around the resonance, and you've got the phase shifts around the resonance. And if you're trying to use some sort of AI with a kind of model predictor corrector, you know, you can get yourself into some corrections that are going to be tough to have a blind AI try and figure out. So, I mean, I think specific to the acoustics and vibration, some of the physics we're dealing with is also tough. There are some, like the cough. I mean, I think that's a great application of it. Some of the other kind of physics that we might be dealing with may just by its nature trip up some of these algorithms.
Yeah, that's a really good point, Lee. And I think back to Gary's point, you know, AI and machine learning have kind of gotten linked to this concept of big data, which I think certainly the computational aspects of machine learning have progressed over the years to allow us to tackle big data problems. But I think if you look at the presentations in the videos and the discussions this morning, what you'll see is a very active area of research here in the application of these techniques is how to leverage these techniques when you really don't have big data, whether that is filling in sparse data or trying to learn from small data sets and then generalize those results. So you can see some of the challenges that people are dealing with.
Yeah,
any other questions or comments on this topic?
I think one guy raised a hand. Question.
Oh, okay.
Hi, this is Kaushik Sampath from NRL. I just wanted to make a comment on this topic in the sense that AI and neural networks are doing a good job with signal processing, or filtering noise out of like real or experimental data. So I think that from like experiments on vibration and acoustics, where you do have you always have unavoidable amounts of noise, this could be a leverage to use to improve the data quality that we get by using the signal processing capabilities of AI. So for example, that would allow us to reduce the resolution of a a raster scan, that we would do if we could, use the improved, signal processing of the AI or something like that.
Okay, yeah, that's a great point. Again, depends on the field, whether the machine learning is doing well or not. Then I guess we can go to the next question, which is more specific to talk about what did well and what didn't get well. Okay, so here I get another. Okay, there we go. Carl, do you want to take this one?
Sure. So our next question for the group is, what are the advantages and challenges for acoustics and vibration of using techniques that are coming from the AI machine learning world? So what do you think are some of the important applied research problems in acoustics and vibration that can benefit from AI and ML? Some examples are inverse problems in acoustics, prognostics in health management, reduced order modeling. And then in addition to, what are some of the problems that can benefit from AI and ML? What are the challenges of using AI and ML for acoustics and vibration applications? I'll turn that over first to our panelists and then to the rest of the folks logged into the roundtable discussion. Panelists, any thoughts on this?
Yeah, I can provide some light on this one, Carl. I think that Lee's question on the last one almost perfectly tees up how practical are some of these solutions, in particular as it relates to prognostics or even diagnostics before we think about prognostics. And I think a lot of times people have this assumption that machine learning and physics-based methods have to be separate. There's this whole field around feature engineering, which is really building a physics-based model to extract information from that system and then allow it to be classified or separated by, maybe something like a support vector machine, which is basically creating planes of separation between your feature sets. So imagine if you're looking at, I used an example earlier of imbalance, if you just send it in raw vibration, which is this, vibration signal that would be difficult to process. Imagine trying to make a machine learning classifier separate imbalance from no imbalance in some, 10,000 dimensional space versus making it separated out once you've taken a Fourier transform and keyed into 1 times the running speed of that system. Now it's only separating based on, the value of one single output. Right. So that is a combination of physics and machine learning where you're actually getting the most value out of that problem. And it's real. It's things that at KCF we're doing today in production. I think that a lot of times the problem is people are so bullish on one or the other that it's either I'm only using physics or I'm only doing deep learning. And they don't realize that if you kind of mesh the two together, you can get a synergy it's pretty powerful.
Yeah, thank you, Montana. I would agree with your comments there. I mean, there's been a long running debate in the machinery health monitoring world between kind of data-driven physics-based methods. And in reality, they're all about data. It's just whether the data is coming from sensors or from a model. Anyone else on the panel?
Yeah, this is Greg here. I'd echo those comments with respect to interest in this notion of physics-informed machine learning, and maybe something to suggest to the university research community is that some of the publications that I've read in that field, they at least come across as being somewhat like computationally difficult to implement in like a practical setting, like if we're trying to monitor a pump or a valve or a reactor or something like that in our industry. And so it seems like there's a spectrum of how strongly physics-based modeling can be tied with data-driven modeling. So I've seen things where, people are doing PDE constrained optimization to come up with the proper like activation functions on a neural network. And chances are for our situations, we might not need something quite as elegant as that, but there might be some things that can be done that are kind of stepping in the direction of coupling together data-driven modeling with physics-based modeling that's not necessarily using like the full state-of-the-art methods. So I think that's something that we would be interested in. And I just also maybe add to this thinking that particularly in a regulated industry like nuclear and probably aerospace and biomedicine and others, the idea of being able to show that we're doing some cool thing with data-driven modeling and machine learning and to be able to defend its credibility, I think the extent to which we could defend its credibility would be enhanced by showing that there's a tie to physics equations or a tie to something that can be verified and validated. So that's an area of interest to me with respect to how can we use all these great tools that are out there, but how can we not only use them, but defend them to ourselves and a regulator that they're indeed credible.
Anyone else have some comments on this?
Hey guys, this is Steve. In case some people have to drop off at 11, there's 2 poll questions that I'm really hoping we get a chance to ask before that happens. Can we just run through those real quick and then maybe kick back into the discussion? And
Sure.
Kelly, if you're there, the first one is for our corporate and government sponsors. Will you be hiring engineers with background in AI and machine learning in the next 3 years? We're really curious about that because that'll help us try to convince students whether to get into that area or not. And then after that one pops up, we're considering starting up a new CAV group in this area. So we'd like your input on that as well. Would you have interest in a group dedicated to bringing you updates on what's happening at Penn State and AI and machine learning and acoustics and vibration applications over the next few years?
So while people are answering that poll, I'll just add one last comment, I think, on this question. And I think one of the things that I've seen is where I think the AI and ML techniques can provide a lot of benefit is that a lot of our acoustic analysis is based on subject matter expertise, looking at things like spectrograms and wavelet plots and recognizing patterns in data that we plot. And that's something that our brains are really adept at. But it's always been very difficult to engineer features to try to extract that out of 2-dimensional information. And when we, with the ability of deep learning neural networks for things like image recognition, it really tries to replicate that function that we're doing in recognizing one pattern versus another in data. And so I think that's a place where we're going to immediately see application of these techniques in acoustics and vibration. One of the challenges is bringing in kind of the additional dimension of sound, because a lot of times everybody who works in this area knows that you look at the results of the plots, but you also can benefit a lot from listening to it. And so bringing in that additional dimension is, I think, is going to be a hot area of research for us in the years to come. Okay, Danny. So it looks like our poll is closed, and we're sharing the results now. So it looks like overwhelmingly everybody says that they expect to hire engineers with background in AI or machine learning over the next 3 years. So thank you for participating in that.
Right. So actually, this connects to our next question, which is what do the industry and the government care? And with this, we would be interested in especially how we should educate our students so that they are prepared for the industry needs. And by the way, I think we have a third poll question, right? Do we want to do that in parallel? Just to make sure we finish that one. And while people answer this question, let's any comments from the panelists for this question?
So I just have one comment based on my experience in academia and industry that if we want to pursue educating our engineers as a machine learning, we have to train them as a machine learning engineers, not data scientists. So basically, if we train them as black box users of machine learning, I don't think it's gonna help a lot, because eventually we need this domain knowledge, physical constraint, or whatever that other members discuss to be integrated in learning process. And it's only possible if we have engineers that they can dig into the algorithm, change the algorithm, make tweaks. If they just use machine learning as a black box, I don't think that synergy is going to happen. So it's always, it would be beneficial if we train them as a machine learning engineers, basically. Because as Carl said, there are two aspects of machine learning. It's representation learning that unifies spectral or other types of feature engineering and model itself. And we always say a good feature, if you can find, is better than a complex model. So I think good features are really important. It can be done by human or learn the features. And that's one thing that I think it's might be beneficial in acoustics, but that requires integrating physical and domain knowledge into machine learning. So we cannot build it and hope that machine learning discovers it by itself. I think it's a little bit hopeless mission. We have to basically tweak the model to be able to do that.
Right. So there are some domain knowledge that's associated with machine learning alone, right? So there has to be someone who really knows what they are using. So
Yeah,
it's
exactly. Yeah, even some of other students that they're system, they're not machine learning, they have a trouble advancing the research because they don't know what's going inside. So why things work? How can I defend my algorithm? Because if you just take data, image data, flip all the labels, you can train a model that fits the data. It's random label. And you can come up, oh, my training is 0, but that doesn't mean anything because you purely learn the noise. How can I verify it? How can I defend that model? How, does it make sense in realistic situations? So I think having this mindset of training them as a machine learning engineers would be beneficial to progress the research.
Yeah, I wanted to add a couple of points on that. I thought it was really powerful, your comment on number one, domain knowledge, just having the ability to actually understand the practical application for those features. The one feature is worth way more than a really complex model. I couldn't agree with that more. The second one around the actual machine learning algorithms themselves, I think that there's been this push lately for like black box analysis where it's like, you know, nobody really understands the way the neural network works. Like you learn how to use TensorFlow, but you've never thought about convex optimization. It's kind of this weird paradigm where everybody goes to the buzz, and really a class in convex optimization and a class in game theory is going to take most of these students far further in their careers than a couple of classes on AI, because I don't really care if you can implement a neural network. I want to know, can you think about developing this geometry that enable us to optimize? I think that that's really, really important. And then the last piece, I think that is something that as someone in industry, I have to take responsibility for, as something that we to a fault do to students, is we expect folks to come on board as both computer scientists or software developers and machine learning engineers. But there has to be somewhere in the middle where academia can meet us, where studying all of these, you know, mathematics-based classes is great, but unless they have some good object-oriented programming background in something like Python or, you know, whatever the specific languages you might want to work with, it's hard for them to take it from their minds and implement it. And a lot of times a lot gets lost in translation when you have someone who studied software engineering versus someone who studied machine learning. It's really hard to have those two meet in the middle. So I would suggest more computer science coursework too for the folks that are studying machine learning, just so that they can practically implement.
Yeah, I agree.
Yeah, I'll just make a comment on this idea of subject matter expertise. There's been a big emphasis in the AI world over the last 5 or 10 years about trying to develop explainable AI, which means that you have AI techniques that you can then dive into and kind of peel the onion back and see why it's making the decisions it's making. But I think you're still going to need a subject matter expert to understand that, or otherwise it's going to be so abstract that the explanation isn't going to mean anything, even though you have it. So you still need the subject matter expertise to figure out why things are happening, and also I think to understand. Eric had to drop out, but he talked about having to generate more data around the noisy conditions because he recognized that the data were sparse there. And if you don't have that subject matter expertise, you won't know whether your data, what direction your data are biased in order to improve the training of these techniques. Should we move on to our next question, Danny?
Yeah, or should we skip to the, well, yeah, we can go on with that. Yeah, although it's a little past the time. So actually here is one thing perhaps Madavi and Montana also both mentioned. It's about in academia, we mainly just look at this tiny bit of a piece in the field of machine learning, that is the algorithm itself. But in reality, we are really having other things to worry about to make sure the machine learning code that works, including the feature extraction and how do we make sure the model is working, namely the verification, and all sorts of things that we, at least the academia, won't think about. So any comments from the panelists? Yeah.
Yeah, this is Tyler. I like this this graphic here, but and one of the challenges coming from, like I say, coming from the experimental side is we've got this whole like data operations problem and infrastructure that we have to if you're not good at dealing with big quantities of data, machine learning is just going to take your huge quantities of data and make more data, and it'll just make the pile bigger. So like, and this kind of gets into where like the big data idea, we have to be careful. Coming in acoustics, we take not kind of Google level quantities of data, but we take a lot of time histories, right? So we can generate terabytes of data for kind of a regular test lab environment. And one of the challenges that we're facing is, the idea of coming up with a neural network to identify whether there's some 60 cycle noise in a signal or something. That's a trivial thing for a neural network to do, but or maybe there's some more interesting feature you're interested in extracting. If you don't have a place to put that new knowledge that you gained, then you might as well not do it. So you have to have you have to be really familiar with databasing and how to store your data, how to make your code reproducible, and do things like version control. There's this technical debt that's in where this graphic comes from, that the acoustics community, and we see it in graduate students and in labs all the time, are like pretty bad at data operations because it hasn't mattered until now. But now when especially if you're treating machine learning as kind of a black box, you have to be putting good stuff into the black box, and then you have to be doing something useful with what comes out the other end. And getting good at data operations is in my view, a prerequisite to doing anything useful with kind of big quantities of data in machine learning.
Yeah, I fully agree with your point. Actually, that's also one reason that I started a machine learning class for aerospace engineering, just to train the students how to play with the data and make good models for their applications. Does anyone, other panelists, have any other comments? Or from the audience?
Goran, this is Goran Pavic. Regarding the question we had of whether CAV should start the subject of AE and ML, I would just like us to remind that we see how focus in our field in vibration and acoustics changes in time from one subject to another. There is a quest for originality and innovation, which sometimes outpowers other criteria. You remember probably that the subjects like active noise control or more recently acoustical black holes are becoming a must. So every decent researcher has to provide his contribution if he wants to be recognized in the field. Yet often the harvest is shy. One German colleague once said, for one of these approaches, we inject kiloamperes and we get out milliamperes. And a huge amount of academic articles and very little concrete stuff. So I'm not saying that the same should apply to machine learning, of course not. But maybe it would be good for us who are still not 100% believers if we could have access to case studies where ML or AI in general has been applied on a problem, but on a real problem in vibration and acoustics. Because we often create, especially in our laboratories, artificial problems to justify using a particular technique, you see. So if we can find real case problems which was successfully resolved using ML, that would be quite helpful, I believe, for answering these questions.
Yeah, Goran, you raise a great point. This is Steve. Yeah, I remember the active control boom and the whole conference has sprung up around it, and it went through the trough of disillusionment shortly afterwards. So, yeah, I think if we do start up a group, we'll have to make sure we're looking at applications that are not contrived to justify the group. And one thing I keep noticing is a lot of stuff popping up in the imaging, the biomedical groups in particular. That looks real to me, and even some other groups. So I think if we do start something up, we want to survey our faculty and students, try to find some good practical stuff and see if it's justified. It looks like there's definitely interest based on the poll result, but I think we need to do some internal work before we decide whether to move forward. But skepticism is always good in forming groups like that.
This is Lee Tito. I just like to frame it this way, in that when you form the group, it almost becomes a, hey, this is a means unto itself kind of decision, where you have plenty of other categories in which the ML and AI can be applied, and by leaving it so that it's not just a singular, hey, we're just focused on the AI part, you say, okay, here's AI applied to an aeroacoustic problem, here it's applied to a vibration problem, here it's applied to an acoustic problem. Inside the current buckets already, you may, by that nature, force it, and you had that graphic just a second ago where it was kind of, you know, one small part of the bigger picture, force it into the bigger picture. Because I do agree that a lot of it tends to be a report on how great we were processing data, not necessarily how great we are creating a capability that can be quickly used by industry, and applied. I think of all of the classical kind of machinery vibration issues you can have, from the signatures in electrical rotor stator signatures. You can have hydrodynamic belt alignment issues. You can have rub and bearing whip, whirl, or wear issues. All of those things are concerns in the industry, and we want to predict them. And so, those, I think we're just kind of reinforcing, those are the kind of outputs where I think that if you try and just have an AI say, okay, let's just take a data set and see how it comes out, you're literally almost saying, hey, I want to predict all of those different responses I can get at one time, as opposed to more of a focused practical application. So creating a new group might be able to still work that problem, but having it focused inside the current groups could also kind of help guide it to more we'll say practical or applicable solutions.
Yeah, that's a good point. And there's always been overlap in all of our CAV groups. So they're not meant to be hard and fast boundaries. But the main benefit to consolidating folks like we've done today is I've learned a lot already. I had no idea of the depth of the stuff that was going on in this field and all the individual groups. I kind of got little bits and pieces of it as I pull things together for newsletters and such. But I think the whole point of a group is to bring the people working in the area together from diverse application fields and share knowledge. And that includes industry and government and internationals. Some of the stuff we saw from KAIST is pretty amazing. Just what works, what doesn't. Hopefully we all start finding things together, avoid dead ends, go down the right paths. So the whole point is if we kind of work together on it, the smarter we'll all get together, the faster we'll get to good tools. But the intent would be not some big master AI ML tool that applies to everything. It's just helping us all get better in our respective fields as best we can by sharing knowledge.
Right, I think we are already quite past the time, so I guess we should wrap up. Carl, do you want to do a summary?
Well, I'd just like to thank everybody for the questions. Thank you to our roundtable panelists for your presentations and your insights. Thank you to the audience. These roundtables only really work when we have good audience participation like we had today. And as Steve said, we'll do some more exploration of whether we're going to form a CAV group. And I'd say to all of our CAV members, be on the lookout for maybe some additional polls to help focus what kinds of things such a group would concentrate on. Danny, I'll turn it over to you, and then we'll let Steve have the final word.
Right, yeah, so yeah, it's great to see all the different opinions from the academia and the industry this time. And apparently, I think there are certain mismatch between the needs of the industry and what we are doing in the academia. So this gives us a lot of hints on maybe where to direct the research, things like this. So yeah, I guess Steve, do you want to finalize?
Yeah, I'd like to actually thank you guys, Carl and Denning, and the panel very much for putting all the time into this and putting the briefs together. Those of you that are watching this after the fact, please, if you have any questions or comments for us, send them our way. Happy to hear from you. It's looking pretty clear that the community thinks this is a real thing and not a fad. There's definitely hiring in this area. That means the CAV and Penn State in general, we need to help provide folks that are smart in this area for you. And hey, if there's any student projects you have in mind, please let us know. We're happy to talk about them with you. So thanks again, everybody, and appreciate you attending this year's CAV workshop.
Bye, everybody.
Bye-bye, everyone.